All right, let's try one. So we're going to evaluate the integral of 2x times e to the x squared dx. We're going to use substitution rule. We're going to try to think out how we actually choose u. So first of all, we kind of look at the different pieces of our function. So just kind of look at the terms here in our function. We have 2x, we have e to the x squared. And usually what happens is we want to identify the more complicated piece. So I would say, out of the couple different pieces here, I would say this e to the x squared is probably the more complicated piece. And so what I'm seeing here is I'm seeing an exponential. We have this exponential function, and then inside this exponential function, inside the exponent, it's not just x, it's x squared. So we have this exponential function with some kind of complicated or more complicated terms inside the exponent. And so my choice for u in step 1, I'm going to try letting u equal those terms that are inside the exponent, the x squared there. All right, so that's the first part. Choose u. Then we calculate du. So once I choose u, then I'm going to calculate du. So I differentiate x squared, I get 2x, and then I multiply by dx. All right. So now we're going to start substituting things in. And while we're kind of getting the hang of using substitution rule, what can be helpful is once you've identified this complicated term, move things around a little bit inside the integral here. So the integral sign always has to come first. The dx always has to come at the end. But we can move these, we can move the 2x and we can move the e to the x squared. We can move those pieces around relative to each other, just as so long as all the variables stay in between the integral sign and the dx. So it can be helpful to take this 2x, kind of our lesser of the terms in here, the least complicated piece, and move it next to the differential. So again, this is not absolutely necessary, but it can be helpful to do this. So I'm going to take this 2x and just move it next door to the dx. And so now when we look at this, we're going to go through and we're going to substitute the values into our original integral. And when we look at this, we have 2x dx here. And just so happens, that's what our du is. So this is going to become du. And then in this complicated term, that's where we're going to be putting in our u term. So that x squared is going to become, we're going to change that over to a u. So when we take our two ingredients that we have from step 1, we're going to substitute them in. So instead of e to the x squared, this is going to become e to the u. And then instead of having 2x dx here at the end, well, that's going to become du. Now, this doesn't always work so perfectly. So sometimes there might be other stuff here with our differential, but for this example, and for the first few that we're doing, the differentials match up very nicely. All right, so we have the integral of e raised to the power u du. And this is what we get after step 2. After we've substituted these values into the original integral. Notice that we started with an integral all in terms of x, and now we have one that's all in terms of u. So there's no x's anywhere here. Now we're ready to integrate. And the integral of e to the u is nice. That's one we can just do. It's just e to the u plus c. And notice I had it there by mistake, and I erased it. Once we find the antiderivative, the integral sign and the differential, they're gone. So once we find our antiderivative, here it is. No more integral sign, no more du. So now this is our function, e raised to the power u plus c. That's what we get after going through finding the antiderivative. We're integrating that new integral in terms of u. We have our antiderivative. The only issue is it's in terms of u, we want it back to x. So that's the very last step, is to convert this back to x. So I'm going to change this u that we have, and I'm going to change it back according to what we said. So instead of u, I'm going to change it back to x squared. So we end up with e raised to the x squared plus c. And that's our antiderivative. And that's after step 4, when we do our conversion back. All right. So that's kind of how this works. And we can always check our work. So if we wanted to make sure we did this correct, we could differentiate our answer. And if we differentiate it, we should get back to where we started. And the way we would do that, this is a special case of the chain rule. We could use the general exponential rule to help us differentiate. So we'll do it for this one, but just keep in mind that for some of the other examples that we're going to do, you can always use the chain rule to help you differentiate, to hopefully check your answer and get back where you started. So let's try it out for this one. We're going to check using our chain rule, or this specific case of the chain rule. So we start with our function, e to the x squared, our answer. We apply the derivative. Derivative of a constant is 0. So what happens when we differentiate an exponential function? Well, the exponential function stays the same, and then we multiply by the derivative of the term in the exponent. So derivative is going to stay the same. It's be the same exponential function, and then we multiply by the derivative of our term in the exponent. So derivative of x squared. And derivative of x squared is 2x. And if we look, we have e to the x squared times 2x, and that's precisely the function we started with, 2x times e to the x squared. Check. So that's just showing that we, hopefully that we did it correctly. So just keep this in mind. We're not going to do this every single time, but if you are unsure of, you get an answer, if you're not sure, you can always check your work by differentiating your answer, and you should get back to the original function. All right, so we're going to try some more examples like this.